remember exactly how to tell him this, but I didn't have my notebook.
Does anybody have any questions? Yes.
4.7, I can't exactly remember which. I think it was the first two mindscapes and then the last one. Because it was about if you stack a stack of papers up, what dimension would you get? 4.7? Yeah, 4.7, I meant to say. And there was the first, yeah.
Okay, so I have a huge stack of papers here in my textbook. What dimension is my textbook?
I thought it was 32. What I put 3 in the D, because I tried writing 3-dimensional, or would it be?
I think you just put the number 3. So a whole stack of papers together makes a textbook, actually. Let me make this smaller so it all fits there.
Oh, okay, so just right there.
What was the next ones?
The one right after.
You take a huge stack of different 12-dimensional spaces and stack them up. We're going to get a 13-dimensional. So we're just following the pattern. A stack of 2D makes a 3D, a stack of 12D makes a 13D. And then did you say the last one?
Yeah.
So we were going to be looking at this today, but we might as well look now. So what we have here in the picture, we have to get the gold bar out of the safe. The break right here in the first two allows you to just bend the corners. So you can stay on the plane itself. You can stay in 2 dimensions like in Flatland, and you can pull the doors open at the hinges. But these don't have any openings at all, the 3rd and 4th pictures. So there's no opening at all. If you follow this band around, there's no opening in it. And you can see there's no opening here. So there's no place to bend the hinge to get a side to flip up. I actually have that doesn't work very well. So we're picturing just taking this door and bending it up at this corner right there. And right here taking this door and bending it at this corner to open it. So the pictures 3 and 4 require actually tearing open an opening. Shouldn't I have a click button here somewhere? Where is it? Okay, we'll take my word for it. Okay. Any other questions? We've been examining the 4th dimension by looking at lower dimensions. We had drawn pictures of Ed and Mike as they would be in 2 dimensions. So if Ed and Mike were in 2 dimensions, they couldn't all fit. So just a cross section of Ed and a cross section of Mike, our authors, would fit in 2 dimensions. Now, when they look at each other, because they're in 2 dimensions, they see each other the same way you would see a coin, not from above, but from head on. So if you looked at a coin and lowered your eyes so that you're on level with the coin, you just see a line. And that's what Ed and Mike's perspective is. They're stuck in the plane and they're seeing each other as a line. In fact, what happens if I put this lasso around Mike? Can Mike see Ed? And no. So Mike is in the lasso and all he sees is the lasso. He cannot see over the lasso. So if this lasso is completely flat and in the first plane, he could kind of maybe push it around a little, but he's trapped in there. I'm not in 2 dimensions though. I'm in 3 dimensions. And because I'm in 3 dimensions, I can let Mike see Ed by just lifting up a little piece, like that. So I can lift up the lasso and then Mike can see Ed. Or I can put it down and say, no, you can't anymore. So this idea of looking from the 3rd dimension down to the 2nd dimension gives us an idea of what it might feel like to look from the 4th dimension down into the 3rd dimension. So if there's someone in the 4th dimension observing us, they have a different view. I mean, look at the view we have as a 3-dimensional beings looking at 2-dimensional. Let me get a marker that writes darker. So we are 3D. Looking at 2D, we see Mike's and Ed's brains. We see their lungs. We see inside of Mike and Ed. So we can see inside Mike and Ed in their 2D fixture, but Mike and Ed don't see that. Even if I take the lasso off, what does Mike see when he looks at Ed?
A line.
Yeah, he just sees a line. And again, it's like our coin. Looking down at 2 dimensions from our 3-dimensional place, we see the whole coin. But if we were trapped in the plane with the coin, we would only see its edge. So that makes us think about, well, if that's similar, and there are 4D creatures, what could the 4D creatures see when they look at us who are in 3D? Okay, so if this analogy holds, as we followed analogies from 0 dimensions to 1, 1 dimension to 2, 2 dimensions to 3, and we saw them holding. So if this analogy holds in the 4th dimension and there's a 4th dimensional person looking at us, what might they see? Let's step back and see, what do you see? Okay, so you're 3D. You're 3D, you're looking at students who are 3D. What do you see when you look at them? Do you see a line? No, you don't see a line. Because you're not 2D, you're 3D. What do you see?
Forms.
Yup, you see the forms, and you see what covers the form, right? That's all you're able to see, is what is covering the form. So you can see the skin, you can see hair, you can see clothes. These are just the outer covering, and the outer covering we talked about is actually 2D, right? So the outer molecules that you're looking at are 2D. Just like the orange, I don't see inside the orange, I see its skin. And I would be able to shave that skin off and flatten it off. Well, I only have to shave it, it's a cutie, it'll peel right off. I could peel it off and flatten it, and you have a 2D image there. So you don't want to, I don't think your neighbor would like you if you took their clothes and flattened them out, but you could, right? You could take that. You take those clothes and flatten them out, and they're 2-dimensional. So, back up here, what do you think a 4D being might see when they looked at the cutie or the halo? Well, they might see inside it, okay? If there was a 4D being looking at us, they might see our insides. I haven't met any 4-dimensional people, so I don't know. But if the analogy holds, then that's what the analogy would be. We are 3D looking at 2D from above, and so we see inside, whereas the 2D beings trapped in the 2-dimensional plane just would see a line if they were looking at each other. So you see the dimensions here. This is 2Ds looking at each other, seeing a 1-dimensional boundary. 3Ds looking at each other, we see a two-dimensional boundary. 4Ds looking at us, seeing the whole 3D, the inside. Okay. Because we look down and we see 2D, we see all what's inside, not just the line on the outside. Okay, well, I think that's kind of fun to speculate. Another homework problem that I don't know if you have, but I will be giving you on your quizzes, is how you could use the fourth dimension to separate knots. So there's some problems like that in your text. Well, maybe I'll just show you some knots first. Okay, so here's some knots. We have a red string, a white string, and a green string knotted together. These are in 3 dimensions, these strings. Now, when we were looking at the lasso that I put around Mike in the plane, I could take this lasso and remove it from the 2nd dimension and bring it up to the 3rd dimension. Does Mike see the lasso when I've lifted it up like this? No, there's part behind him, but Mike doesn't see it anymore. So I can, in effect, make this string disappear from the 2nd dimension by lifting it up to the 3rd dimension from the 2nd dimension. Well, if we could use the 4th dimension in a similar fashion, we could take knots or other things that are together and lift part into the 4th dimension. So if we could access the 4th dimension, we could lift part into the 4th dimension where it would just, in effect, disappear. So if I took this little 1/2 inch of white string and it disappeared in the 4th dimension, I could take this red string and take it off of there. I could take the green string and take it off, and the white string would be separate then. And then I could put the white string back into the 3rd dimension. So that's the kind of question that we're getting at in these mindscapes. Using the 4th dimension, describe how you would unlink the pictured pairs of objects. So we'll go ahead and draw. The first one's easiest to draw, so we'll draw the first one. On your quiz, you'll have a problem like this, or maybe I'll use these drawings on the next page. Okay. So let's go ahead and write that problem down. So we're in 4.7 yet. Describe, using the 4th dimension, describe how you would unlink the pictured objects. So I'll just make a pair of rings caught together, okay? So those are supposed to be linked. So again, we're using the idea that we had with the loop around Mike in the 2nd direction. I, being in the 3rd dimension, can lift it up, and then Mike doesn't see it anymore. So we're going to pick up lift a small portion of one ring into the 4th dimension. Lift a small portion of one ring into the 4th dimension, if we have the 4th dimension available to us. Well, if it does go into the 4th dimension, it disappears from the 3rd dimension. I'll put disappears in quotes, okay, because just like Mike with the lasso, Mike can't see it anymore, but it's there. So it disappears from the 3rd dimension. So then you can slide the other ring off. Because it'll appear like a little piece is gone, and you can slide the ring off through that gap in the third dimension, and then replace the portion that was in the fourth dimension. So I'm sure there was a mathematician on the committee or the group of people working together to produce Doctor Strange, because that is what Doctor Strange is constantly doing. He's constantly making things appear out of one dimension and pop into the third dimension and then get pulled out of the third dimension back. So they're disappearing, presumably, into an alternate dimension. Well, another thing that we talk about to help see if you understand the fourth dimension is just going from dimension to dimension, from second to third dimension. So I have my ping pong ball again somewhere. There it is. So when the ping pong ball was passing through Flatland, the Flatlander could not see the whole ping pong ball. They could only see that portion that was in Flatland. So let's think about what is the shape passing through Flatland as a ping pong ball. Passes through. And I think you have a couple of problems like that in your 4.7 homework, but I could be wrong. So where you're looking at basically cross sections, right? So the ping pong ball passes through the plane. When it first sits on the plane, there's just a point present in the plane, and then as it passes through the plane, a larger circle goes through the plane. Until the ping pong ball exits the plane, and then there's nothing in the plane again. Now for the Flatlanders in the plane, they didn't see the circles. We looking above know that's the cross section of the shape passing through, but what did the Flatlanders see if they just looked? Yeah, they just saw a line. So first they saw a point, and then they see a line getting bigger and bigger, because again, they're trapped here. They can't see from above like we can. Well, I brought some other slices to ask if you can figure out what they are. They're supposed to be slices of cheese. I was supposed to get different cheese and slice it up, and I thought, that's just going to be a mess. So instead I have yellow construction paper. So this is level slices passing through 2 dimensions. What shape did these yellow slices come from? What shape cheese would this have been as you see it pass through a 2-dimensional plane?
So a cylinder?
It'd be a cylinder, yeah. So you can think of them all lined up like this, making a cylinder. Perfect. Let's try another one. Okay, so what shape was this cheese if it was cheese?
A sphere.
Yeah, that'd be a cheese ball. Okay, so the level slices passing through the plane would make this circles getting bigger and then small again. Next one's a little trickier. And there's more than one answer for the next one. What kind of a shape would pass through a plane leaving those types of level slices? Anybody have any ideas? Let's see if I set them vertical. I need more fingers. Okay. If I set them up vertically, what shape are we seeing? Anybody?
Triangle.
Yeah, I was a triangle. I was thinking like a wedge of cheesecake. Like that. That's what I was envisioning. We're going to draw it in 4 dimensions. So we work our way up to draw in 4 dimensions, and we're going to draw a cube in 4 dimensions. This is something I would be asking you to do on a quiz, and it does take a little practice, but it's not too bad. So we're going to draw a cube in dimensions 0 through 4. So we'll start with dimension 0. Remember, what does a cube degenerate to in the 0 dimensions? Yeah, just a point. So there's no degrees of freedom of movement. The first dimension, what does a cube degenerate to there? Good, a line. So we're thinking ink and drag, because that's how we draw as we move up in dimensions. We ink and drag. So we drag in a perpendicular direction, and that makes a new dimension. So I drag in the horizontal direction, and now in the second dimension, we take this horizontal line, and we ink it, and we drag it vertical. So 2 directions, horizontal and vertical. So we just think of this dipped in ink and drag in a perpendicular direction. So now we do that with the 3rd dimension. So we are needing to get skilled at drawing cubes. So let's practice that now, okay? So draw 1 square, and then we offset and draw a 2nd square. Because we're inking the square up and dragging it in a perpendicular direction. We're trying to visualize that out of the page and connect the corners. So you need to be pretty good at drawing the cube, because we're going to do the same thing with the cube now. We're going to take the 3-dimensional cube, which is what we think of a cube as, and we're going to use it to make a 4-dimensional cube. To do that, I have a little video. So this is on D2L content. There's a little bit of material here for the fourth dimension. How many of you have heard of Carl Sagan? Anybody else heard of Carl Sagan? Yeah, he's a very brilliant man. He's talking a little bit about the fourth dimension here. It's a lot like what we talked about in Flatland.
How to draw 4, 5, 6, and 7-dimensional objects. One point has 0 dimensions. Double the points, and you have 1 dimension. Double the points again, and you have 2 dimensions. Double the points again, and you have 3 dimensions. Double the points yet again, and you have 4 dimensions. Skeptical? You're watching this on a flat 2-dimensional computer monitor. In 2 dimensions, it's not possible to have 3 axes, each of which is 90 degrees to the other 2. Yet we accept this picture as a representation of 3 dimensions displayed on a 2-dimensional monitor. In 3 dimensions, it is not possible to have 4 axes, each of which is 90 degrees to the other 3. Yet as with 3 dimensions on a 2-dimensional monitor, we can accept that this is a representation of 4 dimensions. If you remove any one of the 4 axes, you will go back to 3 axes, each of which is 90 degrees to the other 2. Therefore, each of the 4 axes is 90 degrees to each of the other 3. In the same way, we can add a 5th, 6th, or 7th axis, each of which is 90 degrees to all the axes that came before it. Double the points again. And you have 5 dimensions.
Well, I think this goes on quite a ways. We'll just pause at 5 dimensions. We'll work on 4 dimensions. William Shakespeare once wrote, "Her voice was ever lovely, soft, and sweet, an excellent thing in a woman." I always think of that quote when I hear that. Okay, trying to talk like that, but just not working for me. All right, let's go ahead and draw 4 dimensions. So I suggest you take out a straight edge. So we're going to want this to look good, and it gets all sloppy and messed up if you don't use a straight edge at this point. So draw the 2 cubes offset from each other like you saw in the video. So draw your cubes by making 2 offset squares. So you get your 2 offset squares and then connect the corresponding vertices. So once you have one cube to draw in 4 dimensions, you're going to ink that up and drag it, just like we did for all the other moving up in a dimension. So draw your next cube. That one's not going to work for me because I have my front and my back instead of inking and dragging it. You should draw the same orientation so you can look like you just drug it, okay? Like you poured a bunch of ink on it and drug it along. So once you have your 2 cubes, then go ahead and connect corresponding vertices with a different color. Okay, so a different color helps to show how you're dragging one cube full of ink to create another cube perpendicular. You're dragging in a 4th perpendicular direction. So make sure you connect front top right to front top right. I do check for that. Front top left to front top left. Front top back to, did I say front top back? Right back top to right back top, and so on. So corresponding vertices get connected. If you've made too messy, then you can't really tell what's corresponding. Sometimes even when you do these really nicely and really neatly, your vertices that you connect create edges that lie on top of each other, and it's hard to see what's going on. So another color helps to differentiate those edges that are connecting. So I'm going to come along and see how you're doing with those, at least to as few people. Here's a really nice one. I think this was on Wikipedia. So they have a blue square, a blue cube, and a red cube connected with with edges. That would be hard to read. If yours is getting too little, it might need to be bigger. Yeah, sometimes you might have to make them bigger. Does anybody have questions? Sometimes you might have to make them bigger. Definitely use a straight edge. If you use a straight edge and your lines still are, your edges are still lying on top of each other and you can't see that there's 8 connecting edges, then you can specify. You can just write down there's 2 3D cubes connected with 8 edges. So you connect corresponding vertices to each other, and then I can see that even if one of your red lines lies right on top of another red line because of the way you oriented them, I can see that, okay, you are knowing that there's 8 there. So the idea behind the 4D cube is that we're dragging in a 4th perpendicular direction. Does anyone remember how many boundaries they have in the 4D cube? Remember the 1 dimension. Well, go ahead and write down. Can you go ahead and write down what the boundaries are on the 1 dimension, 2 dimension, and 3 dimension? How many boundaries and what are the boundaries comprised of? What shape? So writing the boundaries. So the line had what for boundaries? Anybody? 2 points. Yeah, 2 points keep the lines contained. So his points are one-dimensional. 0-dimensional, rather. Okay. And then the square in 2 dimensions, what did that have for boundaries? 4 lines. Yeah, so it has a line here, 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 and here that come together to enclose the square. So the boundaries there are 4 lines. Those are 2D. How about the 3-dimensional cube? What are its boundaries?
Six squares.
6 squares. Okay, so those are 3D. I keep saying 1 dimension too high. The 4 lines are each 1-dimensional. The 6 squares are each 2-dimensional. So the boundaries on the 4D cube would be how many and what dimension?
Would it be 2 cubes?
They'd be cubes. Definitely cubes. So they're 3D cubes. Because you see how we go up a dimension for the boundaries on each one? And then the number of boundaries, the number of cubes that make this shape, that enclose this 4D cube would be 8. We go 2, 4, 6, 8. 8 3D cubes. Now you can actually see these if you look at this drawing carefully. So you see the blue cube, the red cube, you can see a cube here, another cube here. That one's not as easy to see as the tesseract, the hypercube in your book. So this 4-dimensional cube or this hypercube is drawn in another way that you can draw it. So we're taking here a 2D picture of a 3D object that's representing 4 dimensions. So it has some limitations, namely that you can't exactly get everything perpendicular in 3 dimensions. However, you can see the 8 boundary cubes, which is very nice. So you can see the 8 boundary cubes. There's the inner cube, there's the outer cube, and then there's a cube forming from the faces. So, for example, the bottom face of the inner cube connects to this face, and then these 4 faces on the side. So this is a cube. So all the 6 faces connecting the little cube with the big cube, those faces are parts of cubes. So you have six cubes connecting the little cube with the big cube, and then you have the little cube and the big cube. So these are all, this way and this way both, are ways of trying to draw what you get when you take and add a 4th perpendicular direction. Let's see if we answered your questions. We started the class with questions. Let's see if we answered them. what is the fourth dimension? Okay, so that's a construct that we use as mathematicians regularly, and we see hints of it in the real world as experiments continue and science continues to experiment. How many dimensions are there? Nobody knows right now. I think we talked about 4D movies already, that they're kind of overnamed. Okay, if there are more dimensions, how is the fourth different from the third? So each dimension would add another perpendicular direction. Can we see the fourth dimension? We get little glimpses of it, just like the poor Flatlanders, unable to see out of their second dimension into the third dimension. We have difficulty seeing the fourth dimension, but there are experiments that are bringing little hints of it to us. So what it looks like, it should be perpendicular to the third dimension. It should include another perpendicular direction. The numbers we use to calculate the fourth dimension in math, we do those all the time. For example, in 2 dimensions you have ordered pairs. In 3 dimensions we have ordered triplets. And in mathematicians, we use the upper dimensions all the time, just as a mathematical construct, whenever we have to describe something that has 4 attributes. So it's very useful in math and science. So right now it's useful in math and science, but who knows, as we learn more, who knows how we might actually use it. It'd be interesting to see. The next section is very visual, so those of you who are like to look at things should enjoy this. We're going on to 7.1, which is fractals. How many of you have heard of fractals? Anybody heard of fractals? Fractals have infinite complexity and a sense of self-similarity about them. So the pictures in 7.1 are fractals, and we can get a sense of the self-similarity as we look at this bottom image. So this bottom image goes on to the next page as it delves deeper and deeper into the Mandelbrot fractal. So this is a Mandelbrot fractal, and since it's computer generated, or I should say mathematically generated, because the first one in fact was not computer generated, Mandelbrot envisioned these without the aid of a computer. So we never really got to see the full beautiful picture that comes from these. But what he gives us is a formula that goes on and on and on, so you can go as detailed as you like. So here we take this little tiny square. For some reason this document camera doesn't show it real well. Let me blow it up a bit. We take this little tiny square right here at the meeting of the 2 round shapes and blow it up. It looks like a little zipper there, and we'll blow up a little piece there, so that's blown up here. And we see that this little piece looks like this, and here we'll blow up a little part that catches that curlicue. Let's see if I can fix this so it works better. No, that didn't work. There we go. Okay, so we have this little curlicue blown up from this little square. And then this curlicue gets blown up, this portion on the next page. We'll go here. And then this little square gets blown up to be this part that looks a bit like a starfish. And then this little portion gets blown up to be right here. And then this little portion gets blown up right here. And here you're seeing the sense of self-similarity, because this shape is similar to this shape. And we could delve in more closely on this and see this. So the fractals have infinite detail, and they have a sense of self-similarity about them. These photos are both fractals. They're both generated, and you could see the infinite detail if we were able to zoom in on those. There's natural items that share a sense of self-similarity. So your author actually opens this section by asking, how can you convince your mother you're eating enough broccoli? Well, send her a picture. Only send her the picture on the right, because when you put all these pictures together to scale, you see your broccoli is 3 different pictures. So we have a sense of self-similarity there. Each smaller bunch is similar to the larger bunch. Some other natural items that have that sense of fractal self-similarity include a fern. So one of the things I'll ask you to do is to circle a part of a picture that's self-similar to the rest. So on here, what part of the fern would you circle that looks like the whole fern? So you could circle this leaf. That leaf looks like the whole fern. Or you could circle one of these little bits on the leaf, because that leaf looks like the whole fern as well. So fractals have a sense of self-similarity on different scales. I have a couple of pictures here that I got off the internet of other natural fractal-like shapes. Who knows what that is? Anybody recognize that? Anybody had biology lately? So it's part of your circulatory system. And you can see how if I had just given you this part, you would say, oh, that's part of your circulatory system. It has a sense of self-similarity with the whole. Or if I had just given you this part, or if I had just given you this part. Well, this part you might have been like, I don't know. So it has a sense of self-similarity. Oops, that's not what I was looking for. Where's the other one? Here it is. So a tree also has the same fractal-like sense of self-similarity. If you looked at a whole tree, you see a whole tree, but you could take off a big branch and see on a different scale how the branch resembles the whole tree, and even down to a sub-branch would resemble the whole tree. So those are some natural objects that have that sense of self-similarity. Here we have the Sierpinski triangle. So what part of that would resemble the whole thing? Could you circle part of it that resembles the whole thing? Yeah, you could, huh? You could circle this whole big part, or you could circle this part, or this part, or if you could keep zooming in, you could circle a little tiny part. We see this sense of self-similarity every time the class starts and I start that recording going, right? You see the screen recorded on itself over and over, just like on the quacked wheat here. These fractals are the Mandelbrot sets. They come from the Julian, I said it backwards, these are Julian sets that come from the Mandelbrot set. So after Mandelbrot made that first set that we looked at the bottom of the pages, Julian took it further and made new sets that come out of that. So fractals are very beautiful. Let's write down what they are so that you have a little definition going on. Fractals are infinitely complex patterns that are self-similar across different scales. Fractals are infinitely complex patterns that are self-similar across different scales. They are created by repeating a simple process over and over in an ongoing feedback loop. They are created by repeating a simple process over and over in an ongoing feedback loop. So we will be spending Friday looking at how we can make some fractals. You don't have to hand in anything for section 7.1 except on Wiley Plus. There's no class activities for 7.1. The 4.7 class activity was to hand in a picture of your two-dimensional drawing of your authors. So you should have taken a picture of these guys, your drawings, not mine, and put them in the Dropbox. I'll see you Friday.